we're going to cover some basics on water. Now, again, this is not the first time we've talked about water or the first time that you've learned about water, but there's some basics that are worth exploring to kind of get a better sense of how it's used and why we use it so much. First of all, know that water, it's pretty much everywhere, right? And that's why we like studying it, but also it's kind of nice to use since it's used in a lot of reactions, whether as a medium. Remember that double replacement reactions happen in a watery environment, and so it's important to study how water affects it. But also sometimes used as a reactant, sometimes used as a product where it directly is changed throughout the process of the reaction. It's also used as a standard in comparison to cover and describe how other processes occur. A lot of times values of various properties are compared to what water does. So water, we know that it behaves in a certain way. How does this other substance compare to specifically water? So water, again, has a lot of purposes in and out of the scientific realm. First of all, water, of course, has the formula of H2O. Please make sure you know that has 2 hydrogens and 1 oxygen. And that bond between H and O is a very polar bond and allows for something called hydrogen bonding, which we discussed before. Of course, this bond right here, this is the one we're referring to. This right there is not the hydrogen bond, right? That is, again, a bond that exists between hydrogen and oxygen. That's a bond. That's a regular covalent bond. But the hydrogen bond is actually what happens on this scale, right? So these are your oxygens, the red, the blue on either side. Those are your hydrogens. Here's your red, here's your blue on the other side. The hydrogen bond is an intermolecular force that exists between different molecules of water, not something that exists within the molecule of water as if it were right here. Also, because it is asymmetric, right? Water is not a symmetric molecule in the 3 dimensions. It's only symmetric maybe on a flat surface like you see here on a piece of paper. Because of those two things, it is a very, very polar molecule, very polar substance. The 2 lone pairs in the around the oxygen, so there and there, those 2 are your lone pairs, and they happen to push the bond so that it has a bent angle of 105 degrees. And of course, significant hydrogen bonding is present between other molecules of water, like we said before, right? This is a hydrogen bond, that's a hydrogen bond, that's a hydrogen bond, that's a hydrogen bond. So there's hydrogen bonds that form anywhere all over the place at any given moment. But the important thing is that those hydrogen bonds, this is a very strong type of intermolecular force, a strong type of attraction. And so if you have other substances, right, other comparable substances in terms of similar size, right, hydrogen has a certain mass, oxygen has a certain mass, and together water has a certain mass. But other substances which might have a similar mass to water, they actually won't have the same kind of properties just because water has so much of these hydrogen bonds, which makes it extra different. At room temperature, RT right here, at room temperature, most other substances of a similar size are gases, right? So the kinetic energies of those particles allow them to float about freely as a gas. The intermolecular forces are not making them stick together. As a comparison, though, water does have very strong attractions. And so because these very strong attractions, they more or less overcome those kinetic energy, the motion that the particles might have. Therefore, they become a liquid. They're not a gas, even though most other substances would be gases at that same temperature. On the other hand, we have ice. So we're going to kind of switch gears from water as a liquid, but now water as a solid. So the structure of ice, if you lower the temperatures, right? If you lower the temperatures enough of water, these IMFs then become a lot more important and are the primary influencer as to how the structure appears. And so instead of having a bunch of molecules that float around independently, we now have this IMF, this intermolecular forces that cause the particles to stick and become this more rigid structure. And you see right here on the right side, right, you have these individual water molecules all floating around, some of them sort of in the background there, so they're kind of faded. And these are a little bit more direct and more bold. But again, these hydrogen bonds that exist hold them all in place. So this structure, this rigidity is not there when you're talking about liquids or gases of the form of water. And interestingly enough, this actually forms a hexagonal shape. And this hexagonal shape is actually something you might recognize because if you've ever seen snowflakes, right? Snowflakes, you have them all kind of in this sort of 6-sided figure. That's because even though, right, we don't really see the individual molecules of water that make up the snowflake, on the molecular scale, on this tiny, tiny scale, right, it's actually all based on this hexagonal shape that you see here. And just by the way that they might arrange and the way that they form, on a larger scale, this hexagonal shape expands, or if you look at it on a big scale, it will look like this hexagon that you might see making up the shape of your snowflake. This also allows for empty space, right? So you can kind of see here, there's a lot of empty space in this three-dimensional space right here. Empty space is also important because that then changes the density of your structure. So this allows for the lower density of the solid form versus the liquid form for water. Remember, liquid form, kind of going to the previous slide here, right? This is a chaotic movement, lots and lots of water molecules floating around, and there's no defined structure. So there's not as much empty space between each of these particles here. In comparison, right, there's a lot of empty space between these because there's that structural hexagonal rigidity, and that allows there for there to be a little bit more space. But even for the same number of particles, right? So if you have greater number of particles in the same space, that's going to be more dense. But if you have fewer particles, like you see here for ice, in the same amount of space, that means it's going to be less dense. Most substances, generally speaking, most substances in their solid phase, or other substances like, other compounds, carbon dioxide, calcium, whatever other substance out there, that's going to be more dense as a solid than it is for a liquid. But water is a strange exception where the liquid form is more dense than its solid form, simply because it does adopt this hexagonal shape. A couple other properties of water. One, that is transparent, odorless, tasteless, practically colorless, or anything that is, again, providing any smell or taste from water generally comes from dissolved minerals and gases that are already in there. That's not actually the water itself. And the color, of course, you can see is actually not something you would normally detect if you had just a small sample of it. It appears colorless, but in fact, if you have large samples of it, that's when you see that the bluish or sometimes the greenish that appears. It also has a relatively high normal and relatively high melting and boiling points. Right? So those melting and boiling points are particularly high for something that has that kind of a mass. So comparable substances with the same mass have much lower melting points and much lower boiling points. But again, water has its own thing. And lots of energy change is required to disrupt those IMFs to change phases, right? So there's intermolecular forces that might hold it in place, right? So you're talking about the hexagonal shape that you might see. It takes a lot of energy to disrupt each of these individual attractions that would exist between the individual particles. And so that's why you have a higher melting point of something like ice, whereas something else, like again, just looking at a pure substance like carbon dioxide has a very, very low melting point because it does not take as much energy to disrupt those attractions. Water has really strong attractions. Couple things here, and these are some facts that I think you are familiar with, but it's important to keep track and know what is distinguishing water here. Let's talk about melting and freezing water. Right, we're talking about going from a solid to a liquid, or from a liquid to a solid, going either way. As liquid freezes, right? As the liquid goes from a liquid to a solid, it releases energy. Right? It releases energy so that the solid particles can attach to each other. Whereas on the other hand, right, when solid goes to water, right, going this way, when solid becomes a liquid, it absorbs energy, right? It has to require energy to be put in to make those intermolecular forces effectively break apart, or at least not be as important. So which one's greater? The energy released when 10 grams of liquid freezes, right, liquid water freezes, or the energy absorbed when 10 grams of this sample then melts, right, of the ice melts. Well, it turns out this energy is the same. This amount of energy it takes to melt something is the exact same as it takes that same sample to then freeze. So it's an opposite process, and there shouldn't be any difference in the amount of energy it takes. Now, this is kind of maybe potentially somewhat counterintuitive, but just know that's a fact. Right? Go ahead and rely on that information. Whatever energy it takes to melt is that same amount of energy it takes to freeze of that same sample. Another question that's also a little bit counterintuitive is this one, which results in a temperature change of the sample. So when you melt ice versus when you freeze ice, or when you freeze water to become ice, which one of these requires or results in a temperature change? And this, again, is a little bit counterintuitive, but actually the answer is neither of them. None of them actually have any kind of temperature change as they change phases. Part of that, again, comes down to this, and this is a lot of text here, and I encourage you to pause right now and just give it a read. A couple things you might notice, again, KE is abbreviated as kinetic energy. IMF's there, right? Think of that as the attraction, the stickiness these particles have to each other. But take a second right now. I want you to pause it, and I want you to read this first and make sense of the individual parts that make up this text. Now, I'm going to kind of give you this very, very, very loose sort of diagram that helps you sort of organize this idea. But let's talk about melting and freezing stuff. So I'm going to draw this graph here where this is energy, and then right here is the temperature. So the idea is that most things, when you just increase the energy of it, right, the temperature is also going to go up. But that's usually assuming that this is all the same phase, right? We're assuming that this is all going to be a liquid. This is always going to be a solid. This is always going to be a gas. The temperature that changes is a result of the energy that's put in. But unfortunately, that's not really what happens. And so what I'm going to do is kind of arbitrarily mark this point right here. We know that this is, again, 0 degrees Celsius, right? Or at least we know that the freezing melting point of ice and water is 0 degrees Celsius. I'm going to make that mark right there. So let's say we have a sample that's really, really cold, like a frozen piece of ice. Well, what I'm going to do is kind of start putting in energy, right? So energy, if I say we start right here, I'm going to put in energy and continue to raise this because this is going to be the solid form of water. But then notice how I stop right here at 0 degrees Celsius. So ice is going to absorb the energy, and then the kinetic energy increases until it reaches the melting point. So that's why I stopped it right here at this position. But I continue to add energy, and this is a really weird part, and this is something that kind of is, again, initially counterintuitive, though it might make sense. But as ice continues to absorb energy, it won't warm the molecules anymore. So we're going to absorb some more energy. We're going to keep adding energy. So in fact, this sort of flattens out and plateaus. Instead, this energy that's being put in is now being used to disrupt the IMFs, holding molecules in place. And so again, note that this right here, the temperature is staying constant. We're not making the particles really go any faster. We're really using this to disrupt those individual IMFs that are holding the solid together. And then you continue to add energy to it, right? You'll see that liquid water will collect around the ice, and that liquid water is also going to be at 0 degrees Celsius. So the entire sample, the mixture of both the melting ice and the resulting liquid, all of that's going to stay at 0 degrees Celsius. Eventually, and finally, right, that amount of energy that you put in will make all the entire sample completely melt. So now it's all become liquid. And then again, as you continue to add more energy, right, as it continues to melt, right, it'll eventually melt and completely go to become a liquid form. It will then continue to increase in temperature as you add more and more energy. Right, we'll definitely talk about this energy and more later on, but that's basically what happens. So this is the solid, right? This section right here, that's warming the solid up to 0 degrees Celsius, where it will start to melt. This right here is a mixture of the solid and the liquid as the solid melts and the liquid forms. And then past this point, right, you kind of got this little X here to mark that, is where this past point of added energy, all the added energy will then be used to make the particles move faster as the liquid warms, right, no longer a solid. So again, I want you to keep in mind that this, again, is not a smooth process. This is not something that will just go like that, right? There's definitely kind of this weird break in the middle where, in fact, the particles are not being used to warm up, but in fact are being used to disrupt the IMFs. You can do the same thing now, right? Describing this process of liquid water being placed into a cold environment. So effectively, just take the same idea, right, that is presented at this top part, and now change the appropriate words so that it becomes relevant to liquids becoming an ice. And now, to kind of wrap this up, this is kind of going to go to the other part of phase changes for water. This is now going to talk about vaporizing, condensing water. So remember that vaporizing water, that's going from the liquid to a gas, and the condensing is going the other way from the gas back down to a liquid. So this, again, discussion that we have here, as water vapor condenses, right, we need to kind of keep track of the energy changes. It's going to release energy. It's going to go from a gas back down to a liquid. That's going to be a release of energy. Whereas when liquid vaporizes, it's going to absorb energy to go from the gas, or go from the liquid to become a fast-moving gas with nothing really holding it in place. So this next question, which energy is greater? The energy released when a 10-gram sample of water condenses, or the energy absorbed when a 10-gram sample of liquid evaporates? So once again, in this context, we discussed this before, it should be the same energy, right? It should be the same amount of energy whether it freezes or if it, it's not freezes, but if it vaporizes or it condenses. And then the same thing here. Which one results in the temperature change of a sample? The boiling of water, the condensing of vapor, right, going either way. Again, the temperature is not going to change at all. It's going to stay constant the entire time that sample is undergoing the change. Now, leading up to it, right, as it warms up to start to boil, or as it starts to cool down to start condensing, yeah, that might change temperature. But once it hits that point at which it starts to change, that's actually going to stay constant the whole time. All right, that'll do it.